So in light of Halloween, we have a molecule up here. It's the active ingredient in all of this stuff. What is it? Sugar, right? Okay, I should have asked somebody. Now I don't know who to give it to. Okay, so it's sucrose, table sugar. And the reason why I have it up there is, where did the stapler go? If where's my baseball player? Connor. All right. Throw the baseball to our baseball player. All right. Whose set of laws determine where this baseball is going to go? Whose? Starts with an N. Newton. Right? So you know exactly where this baseball is going to be every moment in time. Right? Its trajectory. So you would think, since we can put a guy on the moon, well, a whole big shuttle thing, right? We can send little spaceships to Mars and have them orbit around and land on. We can do a lot of things. You would think that we would be able to have, at this point, one set of rules that would, explain molecules, explain the chemistry of the really small. But Newton's laws won't work. They fail miserably. So you can't use Newton's laws. You have to use a whole different book. So something should seem fishy. At least it seems fishy to me. We're missing something. Something is wrong in what we're talking about. Because if we really understood the world around us, there should be one book, one set of rules, right? And you apply them to everything. But that's not how it is. That's the big thing that physicists are working on now, is the grand unified theory. And they're talking about string theory and all these things, but right now you can't even test it. So is that a theory or a philosophy? It's kind of interesting. But the point is what we're going to talk about, quantum mechanics or Newton's law. Something is really off and something's wrong. But quantum mechanics, what we're going to talk about, has not been proven wrong yet in the chemistry of the really small, the size of the electron, the size of molecules. If you ever had an MRI, it's because of quantum mechanics. You got that MRI. If you've ever seen scanning STM images, scanning tunneling microscopy, you know those black and white images of like little bed bugs and things? Again, that's quantum mechanics. It's because of quantum mechanics that you can see things like that. It's because of quantum mechanics that my shirt's red, that we can explain why it's red and not blue. So, and the odd thing about quantum mechanics is that when I throw this baseball to Connor, it looks to me like there's only one possibility for this thing. If I give it an initial speed, initial angle, all that, Connor knows exactly where it's going to go, so he can catch it. But if we shrunk it down to the size of an electron, it'd be impossible to catch it. Because there's all these possible paths that are going on at the same time. You don't know. And without all these paths being possible, we're talking about the impossible ones too. It could burrow, it could go through the ceiling and come back down. It could go through the floor and come back up. There's no way you could catch the darn thing. But without these paths being possible, now they're not going to be very likely, but they got to be possible and they will happen. Without taking those into account, you can't explain anything on the world of the really, really small. So it comes down to statistics. And statistics, if you ever had statistics, it's very ambiguous. It's just a bunch of numbers. So it's really hard to have a concept behind all this. With Newton's laws, you have force, you have motion, you have speed, right? Mass. Quantum mechanics, it's all probability. So that's just how it is. So I just we got to suck it up. So in quantum mechanics, here's an example of it. Here's magnesium metal. Okay. Nice and shiny. Here's magnesium metal. It's not shiny anymore. You can just pass it around. It's chopped up into really small particles. All of a sudden, it's not shiny. Its properties changed. Only something like quantum mechanics can really get into explaining what the heck is going on here with colors and reflection and that kind of stuff. So, and then with quantum mechanics, we can start getting into using quantum mechanics to predict properties of molecules. Okay, and for example, with this diagram here, it looks kind of odd, but maybe you've heard of the rule of like dissolves like, right? That certain compounds, they dissolve each other because they're somewhat chemically similar. What does that mean? It pretty much means a picture like this. Where are the electrons hanging out? Where everything's not shared equally at all. The electrons are hanging out more often around certain atoms, and they're indicated in red. And if there's less electrons hanging out, it's indicated by blue. So molecules that are more similar like this would really interact really well with each other and dissolve within one another. Okay, the Bohr model of the atom. So there's a progression in theories. And Giselle, you remember what the Bohr model, do you remember reading about the Bohr model of the atom? Ooh, no, that's worth an almond joy, actually. These are my favorite. Do you hear what she said? You have the nucleus. I don't know, if you don't like coconut, you're screwed. It has a nucleus. Then she said it has those things around it, the orbits, right? So you have the nucleus in the center, where all the what are for an atom? Protons and neutrons, right? And then the electrons can only be in orbits around the nucleus. So maybe here's one. Here's another one. Here's another one. Here's another one. Okay, so that electron flying around, it can only be in one orbit or the other. Okay? Now, this is way wrong. This is not the quantum mechanical picture of an atom at all. Because look at that, electron has a path. We just said all these things they have to take into all these different paths into possible. I mean, you can't even have a trajectory for an electron, because then you'd know where it is as time progresses, right? So that picture is way off. But it's useful. And it's useful because of what I want to show you. So we have to go on a little field trip to see this. So let's go take a look at this quick. You just leave your stuff in here. We'll be right back in about 3 minutes.
You're a little too small.
So for that hydrogen, we saw 3 colors. So that electron could jump from here to here. That might be a color, right? Or here to here, that'd be another color. Or from like this one to that one, that'd be another color. So we should remove some of these, right? I guess there'd be another one where it could jump. Well, that's about it, right? Yeah, so that'd be an example of why this atom could only emit those 3 colors. But the models, like we said, the model's off. It just won't work. So if we finish early, we can go back over there and change the lamp out. If we change the lamp out, let's say instead of using hydrogen, we use oxygen or magnesium or iron or mercury. You just pick an element and you vaporize it and get it in a very high energy state so it emits light. What do you think would change with, what would you see? Would you see the same 3 colors that hydrogen had? No, you just see different colors. But the point is they're going to be only individual colors. You're not going to see a smear of colors, Roy G. Biv, like you did from a lamp. Okay. Now, even a fluorescent lamp, we even saw kind of bright colors. And that's because this is fluorescence. This is emitting light from a gas, just like over there. Except what they did is they coated these tubes with this white powder so that it kind of smears out the colors a little better. But it's still, you still see a lot of bright reds and things. Okay, so quantum mechanics, there's really only one atom. There's only one atom that these equations of quantum mechanics can solve. Okay, what are these equations? They have their little shorthand notations of it, but I don't know, you don't need to know that. But if you've ever seen something like that, that's quantum mechanics type equation stuff. So there's only one atom on the planet that these equations in quantum mechanics can solve. Well, what good is it if it can only solve one? That's kind of crazy. What about the molecules? What about all the other atoms? It's going to make guesses, and the guesses are pretty good. But what's that one atom? What do you think that one atom is?
Helium.
There's something even simpler than helium. Helium has how many electrons? Who says hydrogen? Right? Hydrogen, because there's only how many electrons? It can't get any simpler than that. And it's still a big, ugly, complicated mathematical problem to solve it with just one electron. So hydrogen's the only one. So that means quantum mechanics has solutions to the hydrogen atom. It knows everything there is to know about hydrogen. It knows its energy levels. It knows it can predict chemistry with reactions of hydrogen atom down to the electrons. But you know, it's like I said, everything else is guessing. But it's pretty good at its approximations. So anyway, when you solve the Schrödinger equation for the hydrogen atom, you get a bunch of solutions, and these solutions are referred to as hydrogenic orbitals, and are pictured below. So all it's saying is that how many electrons are in hydrogen again? 1. So as we give this hydrogen more and more energy, as we give that electron in the hydrogen atom more and more energy, look how its distribution changes around the nucleus. It looks like it gets more shape or less shape as you give it more and more energy. More shape, right? As you go this way, it's more and more energy. Okay. And in fact, what I think is really kind of curious is this just looks like a solid sphere, right? It's darkest in the center, and then it gets lighter as it goes out. But look at this guy. This next one, they call it the 2s orbital, right? The 1s is the lowest energy, 2s the next one up. Look at that. Can you see this? There's a white line right there. There's a node. The electron can't, it can be in the very center about the nucleus, and then somehow it can't be in between. Well, if it can't be in between, how did it get there in the first place? See what I'm saying? It's already doing impossible things which we just don't have any concept for. We just can't relate to it. So what statistics says, that's where it's going to be. Okay? So already odd things are happening. So when boiled down, this is what we're really going to be worried about and what we're going to focus on, that these solutions to the hydrogen atom are described using quantum numbers. And we're just going to play around with the quantum numbers and really not worry about the applications of all these things and just kind of be acquainted with the rules and then leave it for more advanced courses to see the applications and actually do some solutions and calculations and all that kind of stuff. Okay. So we're going to try to organize these things. First, let me give you the symbols of these quantum numbers. There's N, cursive L, M sub L, and M sub S. Now that's supposed to be M sub cursive little l. Okay? So the principal, let's give the names next. Okay? This is the principal quantum number. The principal quantum number is N. And it really describes the shell. In other words, the energy. Okay. And so each shell is going to have its own set of other quantum numbers, but that's kind of more than you need to know. So N is a principal quantum number described by the shell. L is the angular momentum quantum number. Angular momentum quantum number described by subshell. Now, what's angular momentum? Right? If I give this ball linear momentum, it flies to Connor, right? How can I give it angular momentum? Yeah, I can spin it. Now, but where do you see angular momentum in your real life? When you're riding a bike, right? That wheel is spinning. Now, think of momentum first. Momentum just wants to have this mass keep going in the same direction, same speed all the time. Angular momentum, it just wants to stay at the same angle all the time, right? Because you have this wheel spinning, it wants to stay at the same angle. That's what keeps you on your bike and from flopping over. Let me show you here. I wonder if I still have it. All right, now, Kenneth, you got to stand up here. So what I'm going to do is I'm going to spin this wheel and hopefully not chop your fingers off. Then I want you just to grab it and then just see what it feels like. Right now, it just flops around, right? But you don't have any angular momentum because it's not moving, right? A bike just sitting there not moving, you're just going to flop over on. But if you get this thing spinning and then grab it. No, don't stick your finger in there. Grab the handle. Now just, got it good?
Yeah.
Now just try twisting it. Bring it up or down.
This is just like a weird. It's really weird.
How do you describe it?
Like as it's spinning, it feels like it's pushing down as I'm moving up.
Yeah, it's resisting your motion, right? It's resisting his twisting, so it keeps it vertical, all right? It keeps it vertical. That's how you can ride a bike. The bigger the wheel or the faster you go, the more angular momentum you have.
What is that a wheel of?
This is from a bicycle. Okay. So that's angular momentum. Angular momentum, really important, because look at this. The electron, that's all the electrons are doing. They're not going in straight lines at all. There's a lot of angular momentum there. So we got to take that type of motion into account. The, uh-oh, lost my pen. Here it is. Okay. Angular momentum quantum number. Magnetic quantum number. And this has to do with line splitting. So if we took a big magnet, like if you go back over to that room we were at and you look at that hydrogen atom, the gas coming from it, and we put a huge magnet around that lamp, that little red line is going to split into, you have to really look close, 2 little red lines. So, and that's due to this quantum number, giving it more states. And then we have our spin quantum number. Our spin quantum number, okay? Oh, sorry. This one was line splitting. Whoops. This one was the number of orbitals. M sub L is the number of orbitals, that's right. Okay, so what are these possible values for all these quantum numbers? What values can they take on? Okay. Yeah, someone said it. That's worth a Heath bar. Right? Mia, you said it again? Man. Okay. 1, 2, 3, 4, 5, 6. So that's what little n can be. And I wish they would stick with that, right? But instead they also have, and it's just history, and so we're sticking to convention. Instead of saying 1, sometimes they say capital K. So n could also be described by capital K. And it's just alphabetical. So instead of 2, it could be capital L, M, N, O, P, right? So the shell. You can have the n equals 1 shell, n equals 2 shell. But instead of saying n equals 2 shell, you could say the capital L shell. So we just have to know how to name it both ways. Our angular momentum quantum number, little l, that goes from, starts at, anybody know? 0. Starts at 0. 0, 1, 2, 3, 4. But little, again, they have little letters for them. Now, they're smaller case and not uppercase. If little l is 0, you could also write what small letter? Yeah, you would think. Wouldn't that be nice? Wouldn't that make sense? Capital K is, yeah, but it's not. It's little s. And then P. And then little d. Right? Isn't it? So if little l is 0, it could be also called s. If little l is 1, it's also called little p. Little l is 2, it's also called little d. So I told you, this stuff is statistics, man. And then it just gets alphabetical after that. Finally, F, G, H, and on. S, P, D, I know. They skipped E for some reason. Isn't that a good question why? I don't know. G, H, and then it goes I. Okay. M sub L. Finally, we're done with the little letters. Now it's just numbers. M sub L can only take, see, well, we'll go over the big picture when we get this done. M sub L can only go from one number to another number. And that number is whatever L is. You make it a negative sign. Like if L is 1, you make it -1 all the way up to positive L. So if little l is 1, or it's an S-type subshell, if L is 1, you go from -1 to +1. So that would be -1, 0, +1. It'd have 3 possible values if that was the case. And M sub S for an electron can only be +0.5. What is it doing that? +0.5 or -0.5. Okay, so why is this so special and what's with all these rules? It's out of these rules that we get those states, that only certain possible energies are possible. So definitely know this table. Because if you know this table, you can do anything I'm going to throw at you on the exam, anything I'm going to throw at you at the homework. So this is what it's starting to look like. How many subshells, and this you have to get used to the language. How many subshells in the capital L shell? subshell was a description for what quantum number? For little l, right? Subshells refers to little l. So what they're asking, how many different little l values are there? And shell was another word for principal quantum number, n, so that this is my n. Okay. Oh, we don't have it up here. Forgot to write it. It's possible values. Kind of important. So L can be 0, 1, 2, 3, 4 on up. But what are its possible values? It can only go from 0 to n minus 1. So if I'm in the L shell manual, what is my principal quantum number, n? If I'm in the L shell, n would have to be not 1. Anybody see it? 2, right? I can't jump that high, right? 2. So if my n is 2, my L is going to go from 0 all the way up to 2 minus 1 is 1. Well, could write it 2 minus 1. So 0 to 1, that means just 0 or 1. 0 or 1. So the answer would be it can be 0 or 1, so it would be 2 of them. There'd be 2 subshells. We should ask, what are they? The answer is 2. And what are the subshells? And you'd like to write just 0 and 1, but they want you to use the letters. So you should write S and P. And not only do they want you to write S and P, they want you to write the principal quantum number out front. So technically it's going to, and we're going to see this later, it's going to be, we said n is 2, so that's going to be 2s and 2p would be the 2 subshells. But they just want to know how many, so our answer is really 2. I just kind of made it more complicated. So see if you can identify how many subshells are in the O shell, and not only identify how many, but go ahead and write them out, what those subshells are. So if you're in the O shell, figure out what the subshells are, the number of them, and what they would be. So Stephen, you following this? If I'm in the O shell, what does that mean to you? Okay, where I got the n equals 2 from, because they said L. So since it's L, first they said shell, so that gets me up to this column. And then they said L, so that means 2. Okay, so now, Stephen, though, I'm not going to let you go that easy. You're in the O shell, so that means what now? N would have to be 5. 5. So you know n is 5. N is 5. So L would go from, Dylan, what to what? 0 to what number? 6 minus 1. Isn't O 5? O is 5. 0 to, yeah, here you go. Watch out, I catch. 0 to 4. So if it's 0 to 4, 0, 1, 2, 3, 4. So that means I would have to have, what? N is 5. So I'd have 5 little letter S. Keep going. 5p, 5d, 5f, 5g. Okay. How about C? How many atomic orbitals in the p subshell? So if you take a look at the description side, Paul, what quantum number is going to give us the answer to this kind of thing? Number of atomic orbitals. According to our table, if you want to know the number of atomic orbitals, it would be m sub L. It would be m sub L. So that's all you figure out. How many m sub L's are there? And that'll tell you the number of orbitals. So if I have little p, that means what? Mia, what does that mean? If I have little p subshell, that means little l is right? If it's a p subshell, right? Because subshell, we're up on this column. And Paul's right. This is where we're going to be looking in the end for our answer. But we got to start somewhere. And they're talking about subshells, so we're really right here. That means little l is going to be 2. 2? Hold it. 1. L is p is 1. Okay. If L is 1, m sub L could be what number to what number? Negative 1 to 1. Negative 1 to 1. So that means negative 1, 0, positive 1. So there's how many? 3. And actually the answers are also up here in these pictures. See how there's only one for these s orbitals, whether it's 1s, 2s, there's always only 1. For the p's, there's always 3. For a d-type orbital, 1, 2, 3, 4, there's 5. And where's that coming from? Because there's 5 different m sub L's, from negative 2 all the way up to positive 2. Okay. Try this one. If the n quantum number of an atomic orbital is 4, what are the possible values of L? And if you get that, go on to B. If I lost you, just ask.
For the test, are we going to have to memorize all this?
Yes, I would know that table.
Okay.
Because if you know that table, you can answer any of these questions. You want to know what the possible values of L are. So what was the rule for that? L goes from 0 to n minus 1. So the only thing you need to know is what little n's going to be. What's the answer? 3. Right? Because you're going to have 0, all the way to 4 minus 1, which is 3. So 0. Oh, there's 4 of them, though, right? I thought 3, too, but yeah, you're right. You forgot to count 0. So the answer's 4. So what are the? Oh, they didn't really care how many. They want to know what the possible values are. So L could be 0, 1, 2, or 3. If L is 3, what are the possible values of M sub L? Did you get that one, Steph? What'd you say? -3 all the way up to +3. So you got to fill in everything in between. All right, pass this over to Steph. How many subshells in the M shell? How would you answer that, Sydney? How many subshells in the M shell? How many subshells in the M shell? So M means that N is... M means that N is what? So do you agree with them? Are you sure? M, yeah, is 3. Okay. So how many subshells would there be? L is going to, because remember, subshells is what, I think what helps me in all of this is to remember what they're asking for. And what they're asking for is what quantum number? What quantum number are they asking for? Subshells is little l. So little l, that always goes from 0 all the way up to n minus 1. So 0 all the way up to 2. So 0, 1, 2. Yeah, 3 total. All right? How many orbitals in the F subshell? Audrey, what'd you guess for that? So F means that what equals what? What little quantum number equals what? What equals 3? Not F, but, well, yeah, F is technically 3, but what quantum number equals 3? Little l. Okay? So then how many orbitals? How many orbitals for? There's going to be a total of? Did we screw up? F. Where's F? No, F is 3. F is 3. Right? F is 3. So how many orbitals? So let's pick on Tanya. How many orbitals? I have to number them out. We're talking about M sub L, and that's going to go from -3 to 3. 7. Yeah, because you get 0 in the middle. 7 total. Okay, so give the notation. Give the notation using letter designation for little l for the subshells. So if n is 3 and l is 2, Lorena, what letter designation would that be? Because they want it to look like their letter designation is something like this, like 1s, 2s, 2p, that kind of thing. That's letter designation. So if n is 3 and l is 2, that would be anybody help her out? 3, not B. Did you say B? I couldn't hear. 3, L is 2 means D. Right? Go back up here. There's 2. 2 is D. 3D. How about 4? Sorry. I picked on Lorena. How about Lauren? Little b. It's got to be principal quantum number is always first. 4. Yeah, n is 4. But you have to say that they want the number, they want the principal quantum number. 4 S. So you say that it's always the principal quantum number and then the letter for a little l. Because L is 0. So they want the principal quantum number. They want the n and then the L. So this one's the number, and that one's the letter. So that'd be 4s. All right. So that's the idea. I think you guys got the idea. So all this, if you know that table, you're set. So have a good weekend and behave yourselves.